Hello all, this is David Linder from themathrooms.com, and I got a problem from our AP Calculus rooms in themathrooms.com, where we get a cohort of students that are going through AP Calc and eventually prepping for the exam. I do problems in these rooms, work with the students for issues that they have. And I worked on this limit problem and it threw me. I ain't gonna lie to you. So I see math and physics and chemistry problems all day long, and usually I grind through them pretty well, but this one, and everyone gets stumped every once in a while. So I'm going to work this problem through. I want you to comment and say if you think it was hard or if you thought this was a joke. This is easy and I'm stupid, which I could be. And actually, in retrospect, this is not that hard of a problem. I should have been able to just, but it threw me, and I'll show you why it did. Okay, so without further ado, let's get this problem set up here. So here's my limit problem that I was working on. I'll read this to you. This is the limit as x approaches 3 from the left of this function. This is a rational function. So the first thing we do with limit problems in calculus is we do a direct substitution, which means we're going to plug 3 right into here. I'm just going to do it like this in the interest of time. So I'm going to put 3 in here. This is going to be 9. So 4 over 27, 12 over 81. 12 over 81 can be simplified to 4 over 27. So in fact, these two things are the same. So you get a 0 over 0 condition. But this is indeterminate form. This is good when you're doing limits because this means the limit exists. So this means if I sketch the graph, I have a removable discontinuity or a hole, and there is a y value to this hole. And if the graph comes together on both sides like this, then the limit will exist. So whatever this y value is, that will be what the limit will evaluate to. Okay, so that's good. That's step 1. Now, typically when you have a complex fraction, what you would do is get common denominators and flip and multiply, and one of the values that make it indeterminate would cancel out. So you get some kind of cancellation in a cousin function. So I started to try to do that, but then I realized that all I could get to was 0 over x squared minus 9. So this is like the limit problem that we're really dealing with. And for some reason, I'm not proud of it. It just, I was unsure of it. I'd never seen a function that looked exactly like this. I'm like, what in the world is this? So we Desmosed it, but that's kind of cheating. So let's just look at this. So what you should do at this point is be like, ooh, okay, analytical methods are going to fall down. Let's think graphically. Okay, so I'm going to make a coordinate axis here and realize that I have domain restrictions at 3 and -3. 1, 2, 3. 1, 2, -3 here. Okay, and then I wonder, is there going to be an asymptote here or a hole? Well, at 3, it's 0 over 0, so therefore it's going to be a hole. So I'll make a hole here and a hole here. And besides -3 and 3, this function will always evaluate to 0 everywhere else. So you get like this. So now the limit problem is very easy to figure because we have a graphical approach here. So all we're going to do is take the limit as x approaches 3 from the left, means we're going to approach this way. And the function wants to evaluate to 0, although it doesn't because there's a hole here, but it approaches, the function output approaches 0 as x approaches 3 from the left. So the answer is 0. So there you have it. A little bit embarrassing, but it got me. So I want you to comment and tell me how you did with the problem, and stay in touch because we are going to do more of these problems. Any problems that I get that I kind of find interesting or that can fuzzle me, I will go through with you. So we'll see you soon. Take care.